Well, hello. My name's John Perham, and in this talk I want to present a tool-based approach to an online version of the first year calculus curriculum using Mathematica. So let's start with my experience and motives. So my first experience with Mathematica and teaching was in developing electronic learning material for two courses at the Maersk Mc-Kinney Møller Institute of the University of Southern Denmark, where I was Professor of Applied Maths for 30 years. Now, these courses were in dynamical systems and analytical mechanics, so they were a bit more advanced than what we're going to talk about today. So from 2000 until the present day, I wanted to do the same thing with the standard freshman calculus course, which I've taught at various times for many years. So my aim for this course was to produce electronic learning material written using the Mathematica notebook interface. I then want to convert this material into video lectures loaded up onto YouTube, which students could download. Assuming that the students own a regular copy of Mathematica and this material, I want them to extract a toolbox from the material and use the material to carry out two large-scale projects during the semester. And these projects are to be delivered as Mathematica notebooks to the lecturer using whatever learning management system the university is operating. As a third project, the students are required to deliver their toolbox. And finally, the students are to pass an oral examination on their toolbox in the presence of an external examiner. And this oral examination can be either taken locally or using Skype if we want to do it remotely. The economics of this method is a greatly reduced budget for presentation of material, but an increased budget for evaluation. I believe that this method of presentation and evaluation provides a rigorous method for holding first-year mathematics education online. Well, that's a lot. So let's proceed. Well, one of the more illuminating experiences of my life was a lecture on curriculum design delivered by, I think, some medical educators at the university in Odense. And according to them, the designer of a curriculum should answer the following three questions in order. In other words, this order. So, question one is, what expertise do we expect the students of this course to acquire? And question two is, how do we evaluate that they have acquired this expertise? And thirdly, what do we teach? Well, old-timers like myself will recognize that in traditional courses, the questions are answered in the reverse order. So, thus, we first choose the textbook to be presented as lectures and tutorials, and then we specify the method of evaluation, and this is usually a handwritten examination. And, we don't really worry about this. 15 years ago, we worried about the concept of competence-based education, but we found it too hard because competence in a traditional course was the ability to pass the written examination. So how should we design a first-year curriculum in calculus? Well, part one. Students should master the basic tools of the calculus and be able to combine them to solve more complex applications. Tools should be implemented in some suitable piece of software. Secondly, students should organize these tools into a toolbox from which they can be extracted to generate reports of more complex applications. The reports of these applications should be submitted using a suitable piece of software and evaluated. And finally, students should undergo an oral examination of their toolbox. Well, the tools are the content of the standard curriculum course, arranged so that tools are only learned once. It's actually taken me 15 years to design this order. And there may be other orders, and many tools of the algebra course are introduced as well. In these 15 years, I've found that the computer algebra system Mathematica is an appropriate software vehicle for all aspects of the course, including the notebook interface enabling the production of the electronic textbook, providing tools for implementing all the mathematical functions and processes, and a tool for reporting projects. Well, what's in the course? Well, there are 5 main topics, the first one is essentially about linear functions and linear equations. The second chapter, if you like, involves us looking at graphics and visualization, the area under curves, and the fundamental theorem of the calculus. The third chapter involves learning about polynomials and rational functions and the inverse of polynomials. They're fairly short, but the next 2 chapters are quite long. And the next chapter involves learning about the exponential and logarithmic functions. And when we've done that, we'll be able to move on to learn about the trigonometric functions. And all this is basically the contents of the standard first-year calculus course. Well, in teaching these or learning about these things, other topics are naturally introduced, including integration and differentiation of functions, the fundamental theorem of the calculus, the inverse function theorem, the method of partial fractions, systems of linear equations, linear differential equations, Taylor series, vectors and matrices, linear transformations, products of matrices, and complex numbers. The exponential function is introduced in a project to calculate the air pressure as a function of altitude, and the trigonometric functions are introduced in connection with circular motion. So to give some idea of the nature of the lecture material, I'll now execute some of the first chapter. So let's get that file. There we are. And that first chapter is called IT Enhanced Freshman Mathematics. So let's go through it. So let's start with the technology of arithmetic. And here's a quote from somewhere. Years ago, if you asked a child what was 2 plus 2, they would reply 4. Later, they would answer, "Let me start up my calculator." More recently, they would need to start up a spreadsheet. Now they would reply, let me Google addition. So, in other words, there's been a transition to more and more technological aspects of doing arithmetic. Well, arithmetic is the age-old process of calculating with numbers. And the problem with arithmetic is that the operations of addition, multiplication, subtraction, and division become more complicated as the size of the numbers increases. For this reason, humans have invented a variety of methods of technologies to aid them in their labours, and these include the abacus, which is still used today, tables of logarithms, the slide rule, mechanical calculators, and this was, let's get rid of this, these were very much the state of the art up to the 1940s. For example, the calculations involved in developing the first nuclear bomb during the Manhattan Project were carried out by an army of clerks using mechanical calculators. The exception was the project going on at Bletchley Park to break the German codes. Here were assembled some of the pioneers of computer science, and debate still rages as to whether their machine Colossus was the first real digital computer. Soon after the end of the war, these pioneers, Max Newman, Tom Kilburn, Alan Turing, returned to the University of Manchester, built the first computer, and the rest is history. So you can see a description of that on this internet address. Well, I was fortunate enough to study for my doctorate there, where I used the Atlas, which was then the largest and fastest computer in the world, and a descendant of the Baby, which was the first computer. Even then, anyone doing complicated calculations with numbers would write a program to do so. However, computers were far from ubiquitous, as well as being difficult to use, so computing was largely restricted to the world of research. Since then, computers have become smaller, more powerful, cheaper, and easier to use. At school, we still don't teach students how to use a slide rule or logarithm tables to do arithmetic, but instead how to use an electronic calculator or a spreadsheet. So let's get on to discussing the representation of mathematical knowledge. Well, the nature of mathematical knowledge lies at the center of the discussion of the nature of mathematical competence. Mathematicians or mathematically competent persons normally learn mathematics from the time they start elementary school and until they depart the learning end of the education system. At various stages of this process, the progress of their learning is assessed through their performance in examinations. At a later stage, they may have been involved in a larger project in mathematics or related disciplines such as engineering or the natural sciences, involving the solution of some mathematical problem and its documentation in a report or dissertation. The quality of such a report is assessed differently from their performance in examinations, because a precondition for the acceptance of the report is the complete correctness of the mathematical reasoning in it. So if we stick to the applications of mathematics and engineering and the natural sciences, then the report will contain mathematical arguments in which the author usually deduces the mathematical consequences of a mathematical model. And this argument will consist of a number of equations which are connected by explanatory text explaining the mathematical operations involved in transforming one equation into the next. And this process is rather like assembling IKEA furniture, in which the hapless owner has to assemble the objects from its components according to the prescribed sequence using the appropriate tools provided. The expert knowledge is not just how to use the tools on the components, but also the sequence in which the operations are to be involved in order to produce a correctly assembled piece of furniture. Well, if we believe this analogy, then mathematical knowledge is not just how to apply the tools in the components to the components, but also which tools and the sequence in which they are applied to produce the solution of the problem. The key to improving the general level of mathematical competence is to teach how to use the tools in a way which improves the student's meta-knowledge, which enables them to use mathematical tools to solve more complex problems. The ability to carry out computations, this is getting tedious, of hitherto impossible complexity got mathematicians to think of computers or of using computers to imitate the process of mathematics, resulting in the rise of the discipline of artificial intelligence. Quite early on, languages, Lisp for example, were invented and software able to manipulate formulas, reduce, develop. This is back in the 60s really. Modern hardware and software called computer algebra systems can be used to carry out calculations with mathematical formulas and symbols rather than numbers. Or can these systems also be used in mathematics education to improve the ability of students to understand and use mathematics? Well, welcome back again. So now let's look at some of the content that I've written for this course. So one of the differences between using a computer to do things and doing them manually is that using a computer we have to be much more precise about what we mean. And one of the first problems we have to look at is what do mathematicians mean by the sign equals. I should say an extended version of this stuff appeared some years ago in the magazine Parabola. Well, the simplest and most common mathematical object is the linear or affine function, which we usually write as this. So notice this is a formula. It looks like mathematics. This is text. Probably the most basically and widely used tool in mathematics is the process of solving a linear equation in one variable x of the type shown below. So what we do is we set this function here equal to 0. And such an equation asks the question, for what values of the symbol x is this relation true? Fortunately, most students can answer this question, which they would write as x equals 3/2. And just to be on the safe side, a student might set x equals 3/2 in the left-hand side of the equation to verify the result is 0. Even though mathematicians pride themselves on the precision of their thought, we see here 3 different uses of the symbol equals, expressing firstly the identity of 2 patterns of symbols, which is this one here. So we set f of x equal to this pattern of symbols here. The second one is to ask the question, for what values of x is this relation true? And the third use is we want to set this value into the left-hand side of the equation. So if we're going to be able to use a computer for carrying out mathematical operations, we need to be more precise. So how does Mathematica represent equality, equations, and assignment? So equality, well, the computer algebra system Mathematica enables us to perform mathematical operations on patterns of symbols by executing code segments. So let's executing the fragment here, f of x equals 2x minus 3. So to execute that, we do this, and we can see that we have an input, and the output is minus 3 plus 2x, which is, well, what this relation does is establish an equality between the symbol f of x and this function here, 2x minus 3, excuse me. So let's execute f of x, and it does indeed produce this function. So the function f of x introduced in the previous section is reminiscent of the normal mathematical notation for functions. In this context, x is normally regarded as a formal parameter, meaning if x is replaced by 2 or t, then the function is evaluated by replacing x by either 2 or t. So we can try this for our function here to see that it doesn't work. In other words, x is not a formal parameter of this function. This is just a collection of 4 symbols, f left bracket x right bracket. Well, this kind of function is implemented in Mathematica in a slightly different way, which can be seen by defining a new function g of x using this. So the only difference is that x is replaced by x underscore, and what does that do? Well, it seems to produce the same thing, but now let's work out what g of 2 is, and we can see that's 1. So if x is 2, this is equal to 2 by 2, which is 4, minus 3, 1. So we can see that the symbol x underscore means that x is a formal parameter and can be replaced by something else. Equations. Well, the question, for what values of the symbol x in the expression here equal to 0, true. It is answered by evaluating the logical expression representing the equation using this. So we have an equation, and this is equal, so this is a collection of symbols, and that's equal to 2x.3 minus 3, and then we've got a double equal sign, 0. So let's see what that means. Well, that's what equation. So now another thing to notice is that in this book, the whole course, all equations will have the form of some function equal to 0. And this has the advantage that we can multiply our equations by any number and we won't change them. In this book, well, equations will always have this form. Sometimes we'll refer to the function to be set equal to 0 and solved as the left-hand side of the equation. Now, Mathematica has a built-in function called solve, and where we have an equation here which has this format and some variable, which in this case would be x. So